Hello, today we are going to get into deep reinforcement learning. So it is basically how an agent figures out by interaction with environment. So for example, on top left, you can see an agent learning how to pick up an object. On top right, you can see an ant trying to learn how to walk. And at the bottom, we have an agent trying to learn how to play blackjack. So here's what we are going to do today. First, we'll break down the definition of reinforcement learning. Then we'll look at the real world examples of rats and slot machines. Then we'll look at the famous multi-arm bandit problem and see how it's everywhere. Then we'll take a look at the explore exploit dilemma and try to understand it in plain English. And then we'll deal with the non-stationary problems. So problems of the world that changes. So you have learned something about the world, but the world itself changed. So how to deal with that? And we'll look at some strategies for balancing explore exploit dilemma, which is greedy and epsilon-greedy, and then we'll run a simple Python code to implement greedy and epsilon-greedy. So what is reinforcement learning? So it's a framework for learning how to act optimally by interaction with an environment and receiving a feedback in the form of rewards. So in reinforcement learning, the agent is not told that the action that you perform was good or bad. It is just given a reward, and based on that, it has to determine if the action was correct or not. So the agent is not told what the correct action is. It has to discover what works best by trial and error. So it is about discovery. So everyday examples of reinforcement learning would be playing games. So we learn how to play a game by making moves and winning or losing and then adjusting our strategy. Animals learn to do tricks by reinforcement learning. So dog gets a treat if it does the thing right and gets nothing if it does not. And humans also learn by this mechanism. So if something is hot and you touch it, you learn not to do that again. Before we had AI in code, BF Skinner was running experiments on in the real world. So in this setting, a mouse is kept in a box which has a lever and a food outlet. When mouse would press the button, food would come out, and over time the mouse would learn to press the lever more often. And this type of conditioning is called operant conditioning. So conditioning through rewards or punishment. Now let us formalize the setup that we have. So there are two big components in an RL setting. One is agent and one is environment. At every time step t, the agent looks at the environment and picks an action AT and performs it by giving it to environment, and the state of the environment changes because of that action and the dynamics of that environment, and it moves to the new state st plus 1, and the agent gets the reward rt plus 1. And at the next step, the agent gets the next state st plus 1 and picks up an action at plus 1, and this loops goes on, and or it can or this can stop if the game ends, and each run of the game is called an episode. So either a task could be episodic, so the game ends with an episode, or it could be non-episodic, that is this loop keeps on going. Now let us consider this situation. Let's say you walk into a casino and there's a slot machine with k arms, and what you want to do is figure out which arm is the best and play it more and more often. You have limited number of pulls. So now let's identify which is the agent. So this robot that's trying to figure out is the agent, the slot machine or the casino is the environment, and the k arms that we can pull are the actions, and these are the rewards that we can get after the pull. In this situation, there is no state, or there is only one state which is a constant, so it is irrelevant in this problem. But normally in the tasks there would be many states, and each of those states could be treated as a separate bandit problem. So the ideas that we develop here can be applied to the uh, tasks that have states. So how do we measure the goodness of a state? So initially we have no idea how good a certain state is. So we try different things randomly, and after each pull, we try to maintain an estimate of the goodness of that arm. And this estimate is called action value of that state. And this helps us in making decisions in the future. So how do we do that? So first we keep a running average of the rewards that we have received, and after each pull we update that average, and that average tells us how good a certain arm is. So let's say you played an arm n times and you got the rewards r1 r2 till rn. So the average action or the action value estimate would be average of those rewards, that is total rewards divided by number of times you played it. And after and the next time you play it, let's you get the next estimate qn plus 1, which is the previous estimate qn plus 1 divided by n plus 1 times the new reward minus the old estimate, which is qn of a. So we get this formula from this steps. So the new estimate is just the previous sum plus the new reward divided by total number of rewards, and we this is so this sum divided by n is qn. So this sum is equal to nqn plus the new reward divided by total number of times we played the arm, and then we do plus qn minus qn and we get to this point. This form is better looking and more efficient, so we don't have to maintain a list of all the rewards that we have got so far. And here you can see the term 1 divided by n plus 1 acts as a step size parameter, and over time this value decreases, and so we give less and less importance to the rewards that are more recent. So initially n is low, so the weight given to this term rn plus 1 minus qn is higher, so it would produce greater change in our estimate of qn. And as time goes on, term or this term is given less weight, and over time the error this term has also kind of decreases. So this term here looks like a step size parameter, and this term here looks like an error, which is the reward minus the our estimate of what reward should be. And over time we expect the qn to move closer and closer to the expected reward. So let's consider this case where the banded probabilities are the probabilities of winning based on an arm are not constant but change over time. This can be a case in the real world as well. Let's say you are trying to do archery and you point towards a target and the wind conditions are changing. So your direction of aim might not change, but still the trajectory of the arrow might still be different. For the same action, you got different outcome. So that for those dynamic environments, we have to give more weight to the rewards that are recent. For that, we use a constant step size parameter called alpha instead of 1 divided by n plus 1, which is decaying over time. The key here is that recent rewards count a lot more than the old ones. If something suddenly gets better or worse, the estimate adjusts quickly. And if you expand out the update, you will see that every new estimate is basically a mix of newest reward and the ones before that, weighted a bit less, and so on. All the way back, but the older rewards get exponentially less importance. Here's the classic problem every reinforcement learning agent faces: to stick with what pays off, or to try something new that could be even better. So on the left we have an arm with question marks, which may lead to a jackpot or nothing or a negative reward. And on the right we have a lever which we know pays off, but we can't be absolutely sure that it's the best one out there. So now we have action values, but how do we pick an action based on the action values and balance the exploration exploitation? So should I go for what I think is best or try something new? Every RL agent and every human faces this dilemma. So there are two simple approaches. First is pick the best option always, and mathematically it is pick an action that maximizes the action value function q of a. So pick any that maximizes q of a, and it is given by this notation argmax a q of a. And second option is pick the best option most of the time and occasionally try something random. Mathematically, it would be pick a random action with a small probability epsilon and with the probability of 1 minus epsilon, pick the action which maximizes the action value. So the first approach is called greedy and second approach is called Epsilon-Greedy. So let's see this in code. Greedy strategy is always pick the action which we think is the best because it has the highest estimated value. It is also called pure exploitation, but the risk is we may never discover the best action if we keep on playing the current best action. We might miss out on the real best action. And the second approach is epsilon greedy. This is simple, effective, and it is very commonly used in reinforcement learning. We start by importing the libraries NumPy for numerical operations and random numbers, and matplotlib for plotting the graphs. We create a bandit class for representing the bandits, which takes a probability p as a parameter, which is the true probability of getting a reward from that bandit. And we have a function play that returns +1 with probability p or 0 with probability 1 minus p. Then we create a list of bandits with winning probability 0.9, 0.1, and 0.5. So this bandit is the best, and we hope our algorithms would be able to find this is the best bandit. Our initial estimates are 0.1, 0.8, and 0.5. These are intentionally misleading, so it's harder for algorithms to find out the best one. And we want to play the game for 500 times. We print the initial estimates. So first is our greedy function, and it takes the bandits, initial estimates, and numplays as input. And first we have initial estimates that we get from here. We have a list for counts, and we maintain a list of rewards, which we will later use to find cumulative reward. Then we play the game 500 times, pick an action greedily using argmax. We get a reward by playing that action, update the number of counts for that action, and update the estimate using the formula that we derived in the slides. And we append the reward to the rewards list and then return estimates, rewards, and counts. We do something similar for epsilon greedy, but instead of choosing the best action all the time, we pick a random action with probability epsilon. So we have the estimates, list of counts, and a list of rewards. With the probability of epsilon, we pick a random action. So we choose a bandit randomly using np.random.choice. And otherwise, we pick the best action using argmax. And then we do the same thing, action according to our estimates. And then we do the same thing as we did in the case of greedy. Then we plot results. So this function takes estimates and rewards that we received over time, and plots a bar graph for estimates and a cumulative reward sum for the rewards. Then we print a comparison table with true probabilities, estimates uh, of greedy and estimates of epsilon-greedy. And using this function, we print the counts of how many times each bandit was pulled by the strategies, and then we call all of those in the main function. So first we uh, play it greedily and plot the results, and then we do the same for epsilon greedy, and then we print the comparison tables for both of them. So here we can see that this is the result of greedy. So the cumulative reward with over 500 terms, 500 pulls was around 250, which is not great, and it estimated the value to be around zero point 0.1, which is not correct, and it played the bandit 3 most of the time. And this is the graph of epsilon greedy. So it was able to estimate the value correctly, which this is around zero point 0.9, and it was able to get the reward of 400 plus over 500 pulls. So let's take a look at what actually happened. So our initial estimates were 0.1, 0.8, and 0.5, according to which the second bandit is the best. So greedy policy kept on choosing the second bandit, but the winning probability of the second bandit was 0.01, 0.1. So therefore it almost always lost, and it it updated the value to be 0, which is close to the true value. After this, after that value fell below the value of the third bandit, it kept choosing the third bandit, and the value of that was 0.5. So it never went below the estimated value of the first bandit, which is 0.1. On the other hand, epsilon greedy policy always explored. Even if it thinks that first bandit is the best, it would still sample some rewards from the other two. And therefore, it did learn the action values that were closer to the true probabilities of the bandits. We can see that Epsilon Greedy picked the best bandit 455 times, but Greedy did not even play the best bandit even once. So that is one issue if you never explore. So let us conclude this video by answering why bother exploring. So Greedy can get lucky and find the best arm right away, but if it gets unlucky, it can get stuck forever on a wrong choice. Epsilon Greedy always explores, so it might waste a few tries, but it never misses the best arm in the long run. So the bottom line is a bit of exploration is cheap insurance against making a bad choice forever.